Artificial intelligence and machine learning is becoming more and more in demand as bulky peripherals are eliminated and devices become smaller and smaller. These devices use AI to interact with humans directly, infer context, and as the internet grows, more and more data comes in, which is harder to process, and AI is used for that as well. Moreover, the AI industry is 200 billion and fast growing with hardware and software with many applications. However, developing AI is difficult. It's not like regular programming. It requires a lot of resources, guesswork, engineers, quality assurance, and computer resources. And the reason is that the AI is a black box. Once you train it, you don't know exactly what it's going to do. Moreover, if you want to modify and update it, you must retrain it from the beginning. And all this is very computational and time intensive. It can take hours, weeks, months, depending on the size of the data set. We've developed the unique AI algorithm that is easier to update. You don't have to, in a sense, rebuild the whole house just to replace a window. This reduces engineering time and computational costs. The connectivity is more transparent and clear box. You can determine the AI functions by looking at the network connections. This reduces quality assurance costs and potential embarrassment. And it works better with big data. Our findings are it learns much faster and can fit in more data with less resources compared to gold standard neural networks. And it's even faster than non-neural network algorithms such as k-nearest neighbors. Now, machine learning and AI methods have both a learning phase and a recognition or inference phase. Popular methods optimize weights so that recognition occurs with a simple multiplication. They may vary by whether they're nonlinearities, but they all encode what we call uniqueness into weights. They do that by performing optimization during learning to find the ideal weights to perform the recognition in this form. This is virtually all the AI that's available now. That's deep learning, recurrent networks, convolution networks, support vector machines, and so on. But the problem is that optimized weights are a black box. You cannot tell what's inside of them, and optimizing over the training data is computationally expensive. Moreover, for any change, training must start from the beginning. And even with a lot of resources, top companies can make embarrassing mistakes, like release AI that categorically doesn't recognize certain humans as human. But determining uniqueness is essential to perform efficient recognition. For example, the unique feature here is important in order to recognize the pattern. And by optimizing during training, the weights for the unique feature increase and the non-unique features decrease. But the problem is that uniqueness changes with context. In this next training example, the features that are unique change. So then the weights have to optimize accordingly. But the problem is you cannot predict uniqueness for all possible contexts from the training sets. So this method of changing the weights is not really clear. Moreover, the most relevant context is during recognition. So we determine uniqueness during recognition instead, when the context is available. And we do this by optimizing during recognition, not during learning. The role of the optimization is to determine network activation, not to learn weights. And the optimization is only on the current pattern that's being recognized, not on all the training data. Thus, it's a large reduction in computational costs. Moreover, we can learn the expected patterns without uniqueness, which makes our weights more transparent and clear box. I studied brain-motivated recognition from all perspectives, have startup experience, have experience with patients, research lab with neurophysiology, cognitive experiments, computational background, and simulation. This may be the next generation of AI. Thank you for listening.